Hey, what's up you guys? This is Ilarian Garbuzov and today we'll have a talk on the deep learning. Let's talk about it! Guys, thank you for watching my videos, and if you like my videos, crash the like button, subscribe and give me a comment what can I do for you next. Deep learning, also known as deep structured learning, is part of a broader family of machine learning methods based on artificial neural networks with representation learning. Learning can be supervised, semi-supervised, or unsupervised. Deep learning architectures such as deep neural networks, deep belief networks, recurrent neural networks, and convolutional neural networks have been applied to fields including computer vision, machine vision, speech recognition, natural language processing, audio recognition, social network filtering, machine translation, bioinformatics, drug design, medical image analysis, material inspection, and board game programs, where they have produced results comparable to and in some cases surpassing human expert performance. Artificial neural networks were inspired by information processing and distributed communication nodes in biological systems. NNs have various differences from biological brains. Specifically, neural networks tend to be static and symbolic, while the biological brain of most living organisms is dynamic, plastic, and analog. The adjective deep in deep learning comes from the use of multiple layers in the network. Early work showed that a linear perceptron cannot be a universal classifier, and then that a network with a non-polynomial activation function with one hidden layer or unbounded width can, on the other hand, so be. Deep learning is a modern variation which is concerned with an unbounded number of layers of bounded size, which permits practical application and optimized implementation while retaining theoretical universality under mild conditions. In deep learning, the layers are also permitted to be heterogeneous and to deviate widely from biologically informed connectionist models, for the sake of efficiency, trainability and understandability when the structured part. Deep learning is a class of machine learning algorithms that uses multiple layers to progressively extract high-level features from the raw input. For example, in image processing, lower layers may identify edges, while higher layers may identify the concepts relevant to a human, such as digits or letters or faces. Most modern deep learning models are based on artificial neural networks, specifically convolutional neural networks, CNNs. Although they can also include propositional formulas or latent variables organized layer-wise in deep generative models, such as the nodes in deep belief networks and deep Boltzmann machines. In deep learning, each level learns to transform its input data into a slightly more abstract and composite representation. In an image recognition application, the raw input may be a matrix of pixels. The first representational layer may abstract the pixels and encode edges. The second layer may compose and encode arrangements of edges. The third layer may encode a nose and eyes. And the fourth layer may recognize that the image contains a face. Importantly, a deep learning process can learn which features to optimally place in which level on its own. Of course, this doesn't completely eliminate the need for hand tuning. For example, varying numbers of layers and layer sizes can provide different degrees of abstraction. The word deep in deep learning refers to the number of layers through which the data is transformed. More precisely, deep learning systems have a substantial credit assignment, path, cap, depth. The cap is the chain of transformations from input to output. Caps describe potentially causal connections between input and output. For a feed-forward neural network, the depth of the caps is that of the network and is the number of hidden layers plus one. For recurrent neural networks, in which a signal may propagate through a layer more than once, the cap depth is potentially unlimited. No universally agreed upon threshold of depth divides shallow learning from deep learning. But most researchers agree that deep learning involves cap depth higher than 2. Cap of depth 2 has been shown to be a universal approximator in the sense that it can emulate any function. Beyond that, more layers don't add to the function approximatability of the network. Deep models are able to extract better features than shallow models, and hence extra layers help in learning the features effectively. Deep learning architectures can be constructed with a greedy layer-by-layer method. Deep learning helps to disentangle these abstractions and pick out which features improve performance. For supervised learning tasks, deep learning methods eliminate feature engineering by translating the data into compact intermediate representations to principal components and derive layered structures that remove redundancy in representation. Deep learning algorithms can be applied to unsupervised learning tasks. This is an important benefit because unlabeled data are more abundant than the labeled data. Examples of deep structures that can be trained in an unsupervised manner are neural history compressors and deep belief networks. Deep neural networks are generally interpreted in terms of the universal approximation theorem or probabilistic inference. The classic universal approximation theorem concerns the capacity of feed-forward neural networks with a single hidden layer of finite size to approximate continuous functions. In 1989, the first proof was published by George Tsibenko for sigmoid activation function and was generalized to feed-forward multi-layer architectures in 1991 by Kurt Hornig. Recent work also showed that universal approximation also holds for non-bounded activation functions, such as the rectified linear unit. The universal approximation theorem for deep neural networks concerns the capacity of networks with bounded width, but the depth is allowed to grow. Liu et al. Proved that if the width of a deep neural network with ReLU activation is strictly larger than the input dimension, then the network can approximate any integrable function. If the width is smaller or equal to the input dimension, then deep neural network is not a universal approximator. The probabilistic interpretation derives from the field of machine learning. It features inference as well as the optimization concepts of training and testing, related to fitting and generalization respectively. More specifically, the probabilistic interpretation considers the activation nonlinearity as a cumulative distribution function. The probabilistic interpretation led to the introduction of dropout as regularizer. In neural networks, the probabilistic interpretation was introduced by researchers including Hopfield, Widrow, and Narendra, and popularized in servers such as the one by Bishop. Thank you. See you tomorrow.